Well, good morning, everybody. For the bulk of us that spend our days, maybe occasionally we review DGAs, or maybe we're responsible for reviewing DGAs. I think the point of having, for example, if you look at some of the studies that have been done, like out of Segray, and you look at the percentage of transformers that that actually had issues, either from a failure standpoint or a repair standpoint, you still go back to a point of you had, for example, a large portion of that might have been winding. Well, what's in windings that really causes things like that? Or ultimately, you end up failing the winding, and a good bit of the time it's the paper, right? So when you break this thing down, I always look at it from the standpoint of a lot of paper. To me, that's winding. A little paper, that could be transformer leads that are wrapped with craft paper, or it could be maybe some outer winding kind of issues that you might have, or what I always use the term, and I guess I heard it somewhere years ago. I'm still using it, bare metal. So when I think of bare metal, I think of contacts or connections, one of those two. So if you go back to the very early days of DGA, so I think if my history is right, this pretty much started in Europe, and by the time it ended up in the U.S., it was around in the 70s, probably the mid 70s to later 70s, let's say, is when it began to be utilized by most of the large utilities, at least in some fashion. And as we've discussed on other calls, we actually, the thing we looked for back then was primarily we'd look and see if we had a settling in the transformer, because of all the things that we knew we shouldn't have, we knew we shouldn't have a settling. So folks think of arcing, they think of acetylene, and if you had a trip, if your transformer tripped out on differential operation, well, one of the first things you wanted to know was, do I have acetylene in the transformer? And that was kind of most of our introduction to DGA. Now, this all, for the U.S., it started with a couple of guys out of, I think, Sacramento at the university there, and Freddie Jacobs, which a lot of us on the call actually do know, and good guy, good chemist, a fantastic chemist, and Ted Hupert. And they both worked together there at the university in Sacramento. So I think it was Puget Sound had a massive failure up in the Northwest. And so what they did was they collected up an oil sample and sent it to the university there in Sacramento. And Freddie and Ted actually took that sample and kind of laid out a lot of the groundwork that we look at today in North America for DGA. Hydrogen, methane, ethane, ethylene, and acetylene. And so those hot metal gases, we understood. I'm sorry, we didn't quite understand to begin with, but the chemists did. So Ted Hupert and Freddie Jacobs understood those fairly well. They were both chemists and had their hands around that, and knew from an information standpoint, based off of what they'd been told about transformers, that these would be good gases to look at because they're temperature related. So early on, before DGA, we used what's called, and many of us still use it today, a transformer combustible gas analyzer. I didn't put any pictures up of these combustible gas analyzers. They were portable. Came in like a suitcase, about yay by yay, wasn't very, very thick. Had a couple of jars of mixture of glycerin and I think distilled water. And you would use them particularly on nitrogen blankets, where you would open the valve a little bit and run some of that into blanket through that device, and then you would turn it off, and then you would mix that up, and then you would bring that gas. Once it equalized, you would bring that gas back through across some filaments, and you would read a combustible gas level. And that's how oftentimes we determined whether or not there was an internal fault. And if the gases were high, had gone up on the transformer, the percent fault gas, well, then we would obviously start doing some offline diagnostic testing to try to sort out where the problem was. So you got to go back to the early days, and by the early days, it doesn't seem like it was all that long ago, but I think it was a long time ago. So late 70s, early 80s was when I got my introduction to the first DGA, and what we looked for in that was hot metal gas. So when you think through what these are, what are hot metal gases, there's still quite a few of us that may not really know what they all are. So we'll talk a little bit about that, why they're important, you know. And then the other thing that we'll discuss is, you know, well, when should I be concerned about them? And some of these are, one or two of these are $64 questions, but we will try to provide a little guidance that'll maybe help those that don't have a wealth of experience with it. And hopefully if you do have a wealth of experience, that you walk away with something today. So the next one is, you know, when should I respond? And that's really a topic we'll spend quite a few minutes on talking about, because that the last two bullets here are the $64 questions. So hot metal gas. These hot metal gases, what are they? Well, they're hydrogen. And why do they call them hot metal? Because they're thermally generated or electrically generated. Hydrogen, methane, ethane, ethylene, and acetylene. And if you look at this chart, which is going to be a little small on your screen maybe, but this vertical line right here is the 150 degrees C mark. Okay, so really what this is saying is that hydrogen will start generating thermally from a thermal standpoint at 150 degrees C, and it continues to generate in volume all the way through the fault zone. The next one, methane, generates up until you hit about, I don't know what temperature that looks like to me, but this is about this is 150. This starts at 250, which is ethane. So it looks like it begins to break off about somewhere in the neighborhood of maybe 300 degrees, somewhere in there, 275. I don't know. It's neither one of those temperatures are good, but take your pick. So you're above 200 degrees, 250 degrees C here when you begin to actually break this gas. And then you have ethane, which will do a buildup and then a break. And then ethylene begins to generate at 350 degrees C. And without arcing, you can thermally generate acetylene if you start hitting temperatures greater than 500 degrees C. Once you get to about 700 degrees, you're in the process flashing over. So a lot of times you'll see some of these gases, and you may see one or two parts of acetylene. Doesn't necessarily mean you flashed over. Could mean that you've just hit the 500 degrees C temperature. Now, neither one of those conditions are good, but just something to consider, because I think a lot of times we think, well, if we see acetylene, we flashed. Not necessarily. So I know, and we've talked about, and we did talk about this when we looked at load tap changers, for example, that when you flash oil and you pull a dissolved gas sample on that, and you look at the relationship of these hot metal gases, you can see plainly an arcing signature, how that forms, what it looks like, how consistent is it. For those that may have not made that call, we may visit about that for a moment as well, but not too much time on that. So when I look at this, I generally think in terms of just a progression, right? So the real question is, why are these gases so important? One, your temperature, and we're going to put a slide up here in a minute and visit a little bit about, what do we normally see with regards to temperature in transformers? So, but they do provide insight into the temperature. So if you start having a buildup of gases, some gases will build, some may not, and you can tell by what gas is active on the temperature range what temperature is going on in that transformer. So it may not be reflected in a winding temperature gauge or a top oil temperature gauge. It could be on a bare metal connection somewhere, like a de-energized tap changer or maybe a lead connection or something. And you may have that heat dissipated before it has time to heat the oil up enough to actually move the gauges on the transformer. So if oftentimes you say, well, I've got, if I look at my DGAs and I'm building a lot of ethylene, I don't have any acetylene, but I've built some of the other gases and I've also started to build quite a bit of ethylene. Well, I know at that point that it's at least 350 degrees C, right? So there are knowns that you can do. So then you look at that and you go, well, I got 350 degrees C, but all my temperatures on my transformer look rather normal. And it's just heat dissipation. So I think it's right there at the connection. So if you get out away from that connection a foot or two, or even inches away from it, that temperature begins to go down. So, but at the connection, it thermally is that hot, and it's actually producing those gases. So if you've ever been a little puzzled by that, well, there you go. Electrical stresses. So when you think of electrical stresses, or at least when I do, I think of partial discharge in particular. Uh, and we'll talk about that a little bit as we go along. So DGA can point to partial discharge. It can also, as we were discussing a second ago, thermal fault progression. So maybe I build a little hydrogen, or maybe I in conjunction with some methane, and I start to build ethane, but maybe I don't see any ethylene or acetylene generated. Well, that tells me the progression of that fault at the moment. From a thermal standpoint, strictly from a temperature standpoint. And interestingly enough, even today, our industry is very focused on this, and they should be. Uh, but this is probably what the industry experts at large know better than anything is thermal. And also, it's what most of us at the utilities probably are the most familiar with is thermal. When we start getting into some of the magic gases like the carbon dioxide gases, and I say magic gases because they're not as well understood. It's not that there's no logic to them. It's just that they're not quite as understood as the hot metal gases are. So in the early days, that's really what we were focused on was thermal gases. Categorize developing faults. Why do you need that? Well, if you start building hot metal gas in a transformer and you begin to, the first thing you're going to want to do is categorize that. And by categorize it, I mean, okay, is this on a connection? Is this on a contact on the de-energized tap changer? Is this, on a lead in that transformer? When you begin to build thermal, the first you really want to categorize it as quickly as possible, because the less understood piece of the transformer, which is the paper, is pretty critical. So if you start to generate 250, 300 degrees C in your winding paper, it's going to last all of a few moments in time. It can't take that kind of heat. So it's important to categorize that fault. Where is this? And that's going to drive us more to how do I respond to it. So, and you can do that. That's doable. A proper response to it, as we just discussed. So that's one of the reasons why these are so important. So if you've never seen an oil molecule, you still haven't seen one, even though you see this up on the screen, because there's a lot of things that go into an oil molecule. But for our purposes here, it is going to demonstrate exactly how much energy it takes to break this oil molecule apart. So when you look at this, one of the first things you're going to see, and you'll see it do it all the way through as it unfolds on the screen, hydrogen. So you'll see H2, you'll see two H's come up here and break off. The very first thing right there at the bottom of your screen. And then you see, and I'm going to turn my pointer on here. There we go. Let's do that. So hydrogen is the first one that comes off. And you can see it breaking off at each of these temperatures because, remember, it generates all the way through the fault zone. The next one is CH4, which is methane. That is a 150 degrees C gas. And then ethane, which is C2H6, breaks off beginning at 250 degrees C. And then you have ethylene. So you notice this bond getting a little stronger. That's C2H4. And then you have C2H2, which is acetylene, very strong bond. So it takes quite a bit of energy to break that off. So when you look at the oil molecule and how this thing begins to break apart under thermal, it helps to understand this equation a little bit. So don't confuse me with a chemist. I'm not, but I've had a few of them walk me through this on occasion, which is really helps gain a little clarity into exactly how much energy it takes to, number one, break that hydrogen molecule off, that methane, ethane, ethylene, and acetylene, right? So higher in temperature you go, the more energy, the greater the impact on the oil molecule. Typical transformer in-service temperature range. So this is one I normally ask every time I'm talking to anyone, a group of people or individuals. Think about the range most of these transformers operate in from a temperature standpoint. And some of them, you can obviously get a lot hotter than what I'm going to put up on the screen. But I'm just looking at it from a overall range standpoint. Where do we normally lie with these transformers? And if you go out in the yard and start looking at transformers, you're probably going to fall somewhere between 20 and 80 degrees C. You may have occasions where you got transformers, and especially I had some down in East Texas that they were, and I'm sure many of you on the call have them, where you've got these transformers that were built back in the 1940s, right, 1930s. And we had those things constantly overloaded to 120%. They'd get a little warm. But the way they designed those transformers back then, you could actually run them a lot hotter. But typically, if you go into a substation today and you look at temperatures on a transformer, top oil, main tank, your windings, you're probably going to find that these things are operating somewhere between 20 and 80 degrees C. Calculated hotspots. I'm not a design engineer by any stretch, transformer design engineer by any stretch of the imagination, but I did beg this question one time overseas, and I've actually asked it in several locations. I've only had 2 people actually raise their hand and go, yeah, I've calculated hotspots before from a design standpoint. The answer I got back was typically these things are in the upper 90s, 90 degrees C, maybe into the early hundreds, but definitely nowhere near 150 degrees C. And since these temperatures began generating at 150 degrees C from a thermal standpoint, and I keep saying thermal because we are going to talk a minute about partial discharge, which can generate well below 150 degrees C. These calculated hotspots in these transformers, so you look at where this transformer is going to operate for its life and where it should be. You're not going to be hitting the 150 degrees C mark. For one thing, paper can't take 150 degrees C. Craft paper can't, not for any length of time. It can take it for a little bit, but if something's not done about it and it stays there, ultimately it's going to destroy the paper. So if you think about paper being saturated with oil and you apply a lot of heat to that, it's just like taking I think I'd have a piece of notebook paper laying in my office somewhere, and I do. You went back 20 years, we'd have loads of it on the desk. But if you take something like this, just a typical piece of paper, and you took a cigarette lighter, which I don't have anymore because I quit years ago, and you wave it underneath the piece of paper, eventually this thing's going to start turning a little bit brown. And if you leave it under there, it's going to begin to turn a little bit black. It's going to get brittle, and if you leave it there long enough, it'll catch on fire. So, and in the process of that, you start destroying that dielectric on that paper. So keeping the temperature right on our winding paper is rather critical, because think about what you can repair in a transformer versus what you can't repair. So if you begin to develop thermal in the transformer and your paper's okay, and so you now know that it's outside the winding, and you you can likely repair that if you get it out before it flashes over and destroys the transformer. And in some cases, you may flash over and still be able to go in and repair it. But as hot metal gas builds in the transformer, if it's not happening in the winding, there's a very good chance you're going to be able to fix that problem if you get in there soon enough to correct it. It's a matter of knowing when to go in so that it becomes visible, right? That's the $64 question. And so when you think about thermal and your paper's okay, but you're generating the thermal, I would say a good 9 out of 10 times you're probably going to be able to repair that. Now, there's going to be instances, and I've seen them, where you've had leads buried up underneath the winding. And those connection points couldn't be, there was no way to access those connections that were overheating. So that transformer had to be untanked anyway. But for the most part, with the bare metal overheating in a transformer, probably repairable. So that's a pretty sizable savings when you start thinking about your transformer. So in light of maybe having to replace that transformer. So why are they important, right? So hydrogen really is the key to PD, partial discharge, and it's it's something that's visible that you can see. And we'll take a little further look at that in a moment. Ethylene is the key to coking, and it's also visible. So every call we've been on up to this point, we've talked about the fact that, and I haven't had anybody send me an email going, no, I hadn't had that experience. If you roll a crew to a problem that you see diagnostically, let's say, and so they go and they trust you, they take your word for it, right? And not to mention the fact they may be reporting to you, so you know they're going to roll. It's a good career move to do what your manager asked you to do. But if you send crews out to work on things or to look for problems that they can't find, it takes down the momentum quite a few notches. So in the early days of load tap changer, we rolled crews on load tap changer DGA to locate problems that were not visible. And the crews became complacent about it. And it really made it difficult when we finally nailed how to look at load tap changer DGA to create some kind of enthusiasm. And you know enthusiasm, right? So enthusiasm is, I'm rolled out to a problem, I drain the LTC or the main tank, take your pick, I open the door, I look inside, I'm not motivated at all. I look inside and I go, well, I don't see anything going on here. You know, there's the lack of motivation. Now, if you believe in the diagnostic, the door opens, you got a flashlight, you got mirrors, you know the problem's there. So now you're going to go look for it. So the key here is if typically if the problem's not visible, it hadn't become fatal yet, unless it's in the winding. So we need to be careful with that. But I'm talking bare metal. If it's not visible yet, it's not fatal yet in most cases. And I only say most cases because I'm sure there's a case out there somewhere that I haven't thought about. But I have yet to see one that if you caught this thing in time, that it wasn't visible. It's a matter of knowing when to go in. So, you know, ethylene really is the key to coking in this thing. So I'll pull this diagnostic graph up of these gases and the fluid temp as well. And you can see you have some fluid temp increase here periodically, but if you look at what's actually being generated here, so here's hydrogen right down here next to ethane. I think that's ethane below it. So they're kind of running hand in hand. Uh, if you look at the main generator here, it's ethylene. And you can see ethylene has begun to really take off. So it's really a key to coking, and we'll talk about why here in a moment. And then acetylene's key to arcing, right? So if you flash something over, you can see the pitting from that. So it's visible, and which I think is really important. So to me, personally, these are my three indicators on bare metal right here. Not just if I generate it, but how I generated it. Tells me when I'm most likely to be able to see the problem or send a crew in and have some level of confidence that they're going to be able to see the problem. Because that's the key to everything, and that's why they're important, in my view. So when should I be concerned? Building a hydrogen with separation from methane. This came out of CFIT 7104. So if you look at this graph right here, this bar chart, you've got quite a bit of hydrogen, you've got a little bit of methane. And the rest of your gases are pretty much flatlined over here. Your acetylene, your ethylene, your ethane. So hydrogen, methane, you've got a pretty good separation distance between those two. That's a pretty good partial discharge signature. And PD at this point can be, with enough of it generated, visible, right? So if you look at PD, some of this is some result. We've talked about PD before. Sometimes you see white, black, white, green substance, all PD, right? And you can generate this below 150 degrees C. So this is a signature that I generally look for partial discharge. Now, you may want to get some external diagnostic equipment, maybe go around the transformer and see if what you're hearing is, if you can get it down to a location and maybe point a crew to this side of the transformer or whatever. But bottom line is, if you begin to generate hydrogen in volume and you're capturing it, and you don't see a lot of movement out of these other gases, you can pretty much take it to the bank. You've got some PD going on in that transformer. So you just need a good separation of relationship here, because they both generated 150 degrees C. So if you're capturing this much hydrogen in the transformer, it's a PD condition. Building of ethylene. So that's another one with some separation from ethane. So what I mean by that is simply, if you have, let's say you start building thermal. So you got a little hydrogen, you got some methane, you got ethane. Ethane starts to grow. And before long, one of the things you might begin to notice is ethane begins to drop a little bit. Ethylene begins to generate. And then you start building that ethylene. Well, that cracking process, and that's what it's called, of ethane gas, of that ethane gas molecule, is what creates coke. And that coke looks something like this, in its worst stages, by the way. This is a good example of a coke buildup. Now, it's been there a while. It's pretty bad shape. And it's not pretty to look at, and every bit of that had to be replaced. But you see this a lot of times on de-energized tap changers. That's the tap changer that is operated with the transformer out of service, for those that may not know. And there's a wheel or a dial or a lever on the side of the transformer that should have a lock on it. While that transformer's in service, that should be locked down. So if you weren't aware of that, and you look around your transformer and you find a wheel, and you find a lever with positions across the top of it, if it doesn't have a lock on it, you might want to put a couple of locks on it. Folks have changed that tap with that transformer energized, as hard as that may be to believe, and it cost them their life. It's not like an on-load tap changer or a load tap changer where it operates automatically in service. So this de-energized tap changer will move at the speed with which you move the handle. So definitely that transformer needs to be out of service, and it's designed to either take winding out or put winding back in. So it depends on what you're trying to accomplish. You're trying to raise the voltage on the secondary or lower the voltage on the secondary. But that is a contact, those contacts on the de-energized tap changer, they'll sometimes come in on the rated tap, and everybody's approved that and said, yep, all right, well, let's go with this tap, but the transformer's brand new, and they'll put it on that tap, and it may stay there forever. So it's these days we begin to see a lot of overheating de-energized tap changers from earlier days of transformer building. So all the way through 50s, 60s, 70s, 80s, you start that vintage of transformer. They've been on tap for so long now, you may start seeing this overheat. So as I look at the building of ethylene with some separation from ethane, you'll start seeing it actively generate. And you'll get some pretty good volume of ethylene. Once you do that, you can pretty much rest assured that your problem is visible. So if you roll somebody to go locate this problem, there's a very good chance they're going to find it and see it with their eyeballs, so which is kind of important. So before responding, you got to know where you stand. How long have I been there? Some of these questions we put up last week. Understand the maintenance history on the transformer. So, and one of the reasons I bring this maintenance history up is because if many of you on this very call probably have had transformers in the past that had a repeated problem. Problem was repaired, guess what? It came back. You ended up with the same issue all over again. Could be a design problem with the transformer, could be the first time this problem happened wasn't repaired correctly, or there was maybe something was over tightened or broke, or there's a ton of ways that you can and avenues that you can go down from a why standpoint. But the point is some of these problems can be repetitive, and it can have everything to do with the maintenance history on that transformer. So it's important to know what's been done to that transformer in the past. What's my preservation system? Again, if I'm generating a partial discharge signature on a breathing transformer, I'm not worried, I'm scared, right? Because hydrogen is a very, very light gas. And so it tries to get out of the transformer. So if you've got a breathing transformer and you're seeing oil saturated with hydrogen, yeah, it may be time to run. So because if it was generating at a slow rate, it would be out of there before you probably even had a chance to detect it, before it could saturate into the oil. You may see a little of that depending upon how quick it's happening. But if I've got a N2 system and I'm replacing the bottle, I'm going to go back to that again. We've talked about this in other sessions. If I've got a nitrogen blanketed transformer and I'm replacing that nitrogen bottle once a week or once a month, or maybe once every 2 or 3 months, you shouldn't be replacing that nitrogen bottle very often at all. I'm sweeping that transformer and degassing it on a frequent basis. Again, if that's happening and I'm building a lot of hydrogen in that transformer, it's time to worry about it, because at the moment what I'm doing is taking a broom and sweeping it out, right? So that would be a little concerning to me. So what's my preservation system? And if it is nitrogen, what's the frequency with which this nitrogen bottle has been replaced in that transformer? And if it's a conservator, you need to know if it's got a rubber bladder or if it's an oil conservator that breathes. Differentiating between active and non-active faults. So a lot of people have gas in the transformer, maybe get a little concerned about that, but nothing's moving. Yeah, it's been there, it has been there for a long time, not too worried about that. Degassing a transformer, so I've seen this over and over again where a transformer's been, I see it more so in some areas than I might see in others, but nonetheless, I see transformers where gassing develops. One of the things people might do is take a transformer out of service and degas it, put it back in, and you and I both know what's going to happen. It's going to start gassing again because it never stopped gassing. We just eliminated that history for the moment. So degassing a transformer fixes nothing. unless you've got so much gas in there, you're worried about the transformer blowing up. Well, if you have that much gas in there, you might want to go in and take a peek at it and see what's wrong with it, because you shouldn't reach that level. So let's talk about responding to this. Be sure it's active. There's a wealth of ways to, and a lot of papers out there that you can look at to give you some, in presentations that are on the internet that you can look at that give you some idea how to look for activity. So temperature and pressure has a lot to do with gas concentration. But I don't see temperature and pressure impacting historical data to the point that I couldn't recognize it was active if it's generating. So if something's generating, it's going up, right? And then if it reaches temperatures that causes that gas to begin to crack and form another gas, then I begin to see that gas go down and the other gas go up. And when you do that, you're moving further up the temperature chart, right? So seeing activity is not one or two parts here and there. Activity is, I got movement going on. I'm hitting 10 parts per million in a 24-hour period. Unless something weird happens, that's probably not temperature and pressure of the oil. It's the temperature of the overheating. And I'm not saying that temperature and pressure don't affect readings. They will move based off temperature and pressure. But I'm just not, I'm thinking, I'm not sure I've ever seen a 10 part per million swing on a transformer in the upward direction, particularly, that wasn't an active overheating. It's a lot like, if I set that piece of paper on fire, if I, it's probably going to burn the whole thing. It's going to progress and keep going and finally burn the whole thing up. We don't normally see these things correcting themselves. It's not like I had overheating and then they get corrected. When you see a situation where the overheating kind of got corrected, it could very well be that it had something to do with load. So if you loaded the transformer up, you might start hitting some of that 150 area, degree C area, and you may start generating a little bit of gas because you've got quite a bit of load on the transformer. And then let's say in the evening that goes down. And the gases may begin to drop a little bit. So you may see some swings along those lines, but it's fairly straightforward to watch something active because it will just keep generating. And if you have any questions, reach out to somebody. Hopefully everybody on the call has my information. You can always fire me off an email and say, I'm looking at this and I'm having a bit of a struggle. I'll be more than happy to help. Be sure it's not in the winding paper before doing anything else. So categorizing this fault. Now, I haven't looked at the chat box yet, and it's about time to, but I'm betting somebody may have asked a question about, how do I know when it's in the paper? Years ago, we used to say, well, if you see it just carbon monoxide, CO, begin increasing, then you may have something wrong in the paper. Now, if you apply thermal to paper, you are without doubt going to generate carbon monoxide. There is no question about it. But the thing that I think that we probably should recognize is that carbon monoxide increases may not be tied to paper. That's a possibility. So for me, what I tend to look for when I see hot metal gas rising, I go over and I divide CO into CO2, carbon dioxide, carbon monoxide into carbon dioxide, and I look and I see what kind of negative impact did I have on that ratio, or did I have any negative impact? If I didn't, then I'm pretty sure I'm bare metal. This is a bare metal problem. If I did have a huge negative impact on this ratio, I'm pretty sure I'm in the winding. Or if I had a smaller drop, let's say a 30-35% drop on that carbon oxide ratio, as opposed to a 65 or 70% drop, I may have a paper wrap lead where that overheating is happening. So knowing not so much the carbon monoxide level, but knowing the impact on that ratio can tell you exactly categorically where this problem is. So, and that's something we can talk about in a lot more detail at another day. But there is a way to categorize these faults. Now, look, there's nothing that's 100% out there, and I don't even think the carbon oxide ratio is 100%. But when I think about where I was and where the industry was 15 years ago, and our accuracy for predicting where these faults were located in the transformer, and did a little research and discovered that almost all of these problems either are a lot of paper, a little paper, or no paper. And if you broke them up in those categories and you looked at the failure charts, yeah, there's some other things like the core, and there's other slivers in that graph that the study that Seagrave did, but they're very, very small percentages. So for our whole entire career, we may never see one of those. 90-something% of what we're going to see is either paper, little paper, lead, right, or bare metal. That's the bulk of what we're going to deal with. We weren't all that accurate in predicting paper problems 15 years ago. Utilizing this ratio, we bumped that up, whatever that percent accuracy was, and it wasn't that great in my opinion. We bumped it up over 90%. I think we're pretty accurate with that thing now. So we're able to actually tell where this problem is. So this is all about improving the odds, right? If the problem is in a winding paper, you know, you would, excuse me, want to take immediate action because that winding paper is kind of important. If you damage winding paper, that transformer is coming off the pad, and it's going to get replaced, and it gets expensive. If you catch it early enough, there are things that you probably can do. And by the way, I've seen several transformers where the paper was going bad in the transformer, and only within the last month or so did any hot metal gas start to generate. So if you catch it before thermal starts hitting, you have a much better opportunity of drying your paper out and getting the transformer right and processing it, maybe getting another 20 years out of the transformer. So these are all important points, and I realize that that's going to involve a little longer conversation, but categorizing these faults, make it easy, make it simple, because that's 90-something+% of what you're going to deal with on a daily basis. A lot of paper, a little paper, no paper. And if you do that, and you maybe were a little on the edge about your accuracy and how good you thought you might be with DGA, that will drastically improve it if you have not looked at it from that perspective. So once paper's been eliminated, it needs to be a buildup in order to see the issue. So 3 or 4 parts of ethylene is going to get you nowhere. What you need to see is activity going on with ethylene. You certainly want to catch it before it starts generating acetylene, but you want a pretty good volume of ethylene. So you say, how much volume? Well, let's think about this. So I have a bushing out there. I'm running an offline power factor on this bushing, and it was 0.6%. Now it's 1.9%. Okay? And so I look at that. And so that capacitor went from 0.6 to 1.9. When is it going to fail? When should I take this bushing out of service? Well, one of the things we do with bushings when we see that kind of jump is we immediately replace them, because just putting them back in service and energizing them, that hit on that bushing may fail it right there on the spot. And these capacitors, which is really what they are designed to be current voltage 90 degrees out of phase across that capacitor. That's how you move power. So an increase in power factor is dangerous. So the higher the power factor on a bushing, the worse that bushing is. When's it going to fail? You don't know. It may go to 5% before it finally flashes over. So why does it do that? Because the dielectric gets destroyed, right? So if the dielectric's being destroyed, you don't know in the bushing exactly how much of that dielectric's actually been destroyed. You only know it has been. So how much gas do you need to see in the transformer before you take action? If you are low on your gassing, and suddenly you begin to build a little hydrogen, methane, ethane, ethylene. Suddenly it really starts building in that transformer, and it really starts growing to the tune of, I built up 100 or 200 parts of ethylene. I'm probably thinking I can see it at that point. Now, it could be the size of the tip of your finger. It could be something the size of your palm of your hand. It's hard to say. We've seen low tap changes where we've had huge buildup of ethylene dominating acetylene in a low tap changer. And we knew there was coke in there. And we had to move the contacts, and you could see the coke a little bit. So, and we had, it's been years ago, but I'm thinking of one of the selector contacts. We actually had to get the contacts between, put a mirror back there to be able to see where that was at. That one contact was with something about the size of the tip of your finger was producing that much ethylene in the LTC. So hopefully your first time out, if you try this and with some success, that the crews are actually able to see it, because normally you can see it with the naked eye. You may have to move something, but it can be seen. So is there a hard number there? No, there's not a hard number. There is a buildup of that gas that to the point that you finally can't take it anymore, and you go, all right, right here's where we need to go into this transformer. I don't think it's 75 ppm, if that helps. I think you're into triple digits before you do something like that. But the second you start generating that ethylene gas, if you begin to generate any acetylene at all, right then's the time to do it, because you know you've now crossed over. Something may be preventing the saturation of ethylene in that oil, and now you begin to see a little bit of acetylene there. And when you see that, you definitely want to pull it out. You know it's visible. But along that avenue, most of the time, that's not what happens. You build up 100, 200, 300 parts of ethylene. At that point, you go, all right, I think we can see this now. I'm going to pull it out of service. Just like power factor on bushing, which we talked about. So the right questions: what should I know ahead of time? The gas trend, current and active faults, temperature and load swings can play a part in it, so you got to be careful with that. Leaks, which we've talked about, and past issues. And then never assume anything. It's an acronym, right? So with that, when is the right time to supplement with electrical testing? And that's a really good point, because if you're looking at bare metal overheating on this, it's a fantastic question. You are much less likely to find this with the likes of power factor testing or any of that. What you might find it with, would be winding resistance. Be able to do that. You might see that the connection has enough resistance in that connection that you can actually see that through your winding resistance. Yeah, you might see an increase and actually be able to nail it down to a phase. I've actually done that before once back many years ago when I had darker hair and I had a better body. And I was at a transformer in, if anybody knows where Sulphur Springs, Texas is, I had gone up to that district, and we were looking at a transformer that was overheating, and we were actually able to do a winding resistance, and we noticed that we had a phase that was actually a lot higher. So we knew about what phase this problem was probably on. Pop the transformer open, you could see the coke buildup. So with the paper, the one thing you want to do, if you can catch it before you lose the paper, power factor ought to tell us that, right? So if you don't destroy that turn, you should be able to see that deterioration with offline power factor. And should see an increase. And 90% of the time, these things are on the load side in a distribution station. So, because that's the winding that takes most of the abuse. But power factor is the right tool for that. So when you begin to see that and you get that transformer out of service, and you surely want to run a power factor and take a look at that, because it could be you've got some contaminants, some moisture, you got something, right? So you really nailed it there with the insulation resistance is a good one, but also power factor testing is another one for the paper. When you get into bare metal, I think one of the better hopes is probably winding resistance, where you might see that increase, if that helps. It's a little tricky. This all is a little tricky, which is why you need to do it on some routine basis at your company, because you need to be in front of this data fairly regularly so you can watch this puzzle and get it to kind of have it make a little better sense to you, because the more frequently you look at it, the easier this puzzle begins to come together, and the easier you get more of what I'll call a gut feel for when I need to open something up and look at it, or when I need to respond to it. Some of this is not so much a gut feel. So descending carbon oxide ratios, that's not a gut feel. I descend down to 60, 65%. The transformer's coming out of service. I want to see it. I want to see a power factor on it. The bare metal issues and the lead issues, that's a whole nother thing. So particularly the bare metal issues, folks. So when you think about bare metal overheating, sometimes you have to lean into your intuition as you're watching that gas climb. There is not a hard number any more than there is a hard number for a bushing power factor. Now, if you went from 0.6 on a bushing percent power factor to a 1.9, I don't need my gut to tell me too much. I think I've got my answer. This thing needs to come out now. Now, there's times when maybe you can't get it out, so you are going to, we have what's called, what do they call that? Calculated risk. And but you want to do it eyes wide open and be able to explain the decision, because I think if there's one thing I left the utility with was being able to explain my decisions, and I felt like was not really something I wanted to put in a report. I wanted to have some hard evidence, some past evidence to associate with those decisions, and never just one test, right? That's one of the first things you learn. If you go to more than one test, if you only utilize one test to try to find the problem and you don't have something to corroborate that, you're probably going to be explaining yourself once again. And I never felt good about trying to explain something when I find myself in the middle of it sometimes, and all of a sudden in the middle of it I'd realize I couldn't explain it. Right? That's not the time to discover that you can't explain it. The time to get that is on the front end and ahead of time. So I hope that gives a little bit of insight. I don't freak out when I see ethylene. Can you share more thoughts on portable combustible gas analyzers? Pros and cons. So I like them in conjunction with, right? Because it's another tool. Kumar, it's something to add to the arsenal. So if you've got a nitrogen blanketed transformer in particular, and you've got a fleet of them, these are nice little checks to run periodically, especially if you've got a transformer out there you don't have any online monitoring on it. You may want to do a combustible gas reading on it between your lab samples. If you have I know a lot of people are using network transformers. Use them on network transformers, vault transformers. I don't know how comfortable I am going in a vault and doing something like that, but nonetheless, they use them in vault transformers. But in the substations, it's what we originally used. Now, we'll give you a percent combustible gas level in that transformer, and different manufacturers measure different combustibles, so to speak, but they're all good and give you a heads up to an issue. So if you've got transformers you're still doing annual DGA on, and you'd like to plug a hole there somewhere, or at least try to give some plug to it till you can get online monitoring or something on that transformer, maybe it's in an area where it's not considered super critical or whatever. These are nice devices to have. So you just connect them to the headspace, run the gas through it. Be sure and turn that back off. And I think Arbiter makes one. I don't know these folks. I'm not getting a commission. Cooper brought out the old McGraws. I think it's a good practice. So We're a little past time, but I do want to bring up. So you said we're thinking about making this a standard practice with follow-up and investigative work. I think it's a good one, but it's another thing that I've begun to find now. Some of you do this already, but if you do work on a transformer and uh, anytime you're in that transformer, you replace a bushing, you've gone down in there, fixed a problem, you do that kind of thing. Before that transformer goes back in service, there should, after it's been processed and it's been filled and it's set for its stand time, there should be a DGA pulled on that transformer before it ever gets energized. And the reason for that is if you put it back in service and there was any gas left over, it shows up after you've energized it, you don't know where it came from, and you don't know if that's now or if it was in there to begin with, and that can really cause you a lot of stress. A DGA before energizing, I always do a DGA 1 hour after it's energized. Do it another 8 hours after it's energized. Do it after you put load on it. You certainly want to do it an hour after load. You want to do it 8 hours after load. Then you want to start the 24, 48, 72, and make sure you've got DGAs on these things. Where you don't have online monitors, you definitely want to be pulling those in a regiment of samples. When do most problems occur? After we quit working on things, right? So we get out of a circuit breaker. That's when we're most likely and most prone to a problem. Particularly whether it's routine maintenance or it's there for repair. So I like the portables. I think they're good. I think they serve a purpose. They can serve a purpose. It's another tool. Any tool you can get and add to your arsenal that you think makes you more successful, I say go for it. Well, all right, everybody. Well, I appreciate you joining the call. Everybody have a good one. Thank you for your time. Very much appreciated.